Welcome linear algebra fans. Our last video in this section on eigenvalues, a video on characteristic two matrices might have called similarity and a property called diagonalization. So we'll first talk about similar matrices, a definition, and then explore that definition a little bit. We'll talk about some properties of similar matrices. We'll see how similar to a diagonal matrix is a special property some matrices have. We'll see how to find that similarity transformation when a matrix has a property, and then you'll get to explore briefly a Fibonacci sequence. Pretty fun. So as we frequently do, we'll start here with the definition. We say that A and B are similar if there's a non-singular matrix S such that A is equal to S inverse times B times S. Okay, a couple observations here. We often say that A is similar to B through S. We'll show that A similar to B implies that B is similar to A, so often we'll just say that A and B are similar. Okay, it's sort of quick to construct such a similarity relationship. Here's a matrix B, a 5 by 5 matrix, and a matrix S that's a 5 by 5 matrix. It's a little bit of a mess, but one can quickly, via Sage maybe, find the inverse of S and compute S inverse times B times S. And we'll call this matrix A, and we can see that by construction then, that A and B are similar. Okay, let's have a look at this with sort of a different example. Here's a matrix B that we've looked at before. We looked at this in our section on eigenvalues and eigenvectors. And the matrix S, I'll let you verify this on the worksheet. It turns out that this matrix D, that I'm calling D, this is a matrix D, is a matrix that's similar to the matrix B. Now, a couple of observations. The first observation is that D is a diagonal matrix. That's a pretty interesting form. We'll talk about this more in a minute. Elements on the diagonal and zeros elsewhere. We've found eigenvalues of the matrix B. The characteristic polynomial of B is minus quantity, x minus 3 times x plus 1 quantity squared. It turns out that the characteristic polynomial of D is really quick to find. It's the same. And moreover, eigenvectors of D are really fast to identify too. So I'll let you think about that for a minute. But you should find that eigenvectors of D are in fact just the unit vectors in C3. Okay, so let's go ahead and check out properties of similar matrices. We'll start off with a theorem that shows that this property of similarity is what's called an equivalence relation. So the matrices aren't equal, but if A is similar to B, then B is similar to A. Of course, A is similar to itself. And there's this transitive property, right? If A is similar to B and B is similar to C, then A is also similar to C. Okay, so this identity property, this reflexive property, and this transitive property are characteristic of an equivalence relation. So for the first property, of course, the identity matrix has inverse identity matrix. So we can see pretty quickly that A is equal to the inverse of the identity times A times the identity. Hence, A is similar to itself. For the second property, this reflexive property, if A is similar to B, we know that there's some matrix S such that A is equal to S inverse times B times S. Let's take T to be S inverse. So when A is similar to B through S, it turns out that B is similar to A through T, or S inverse. Okay, similarly, for this transitive property, let us suppose that A is similar to B and B is similar to C. If A is similar to B through S and B is similar to C through R, we can see that A is equal to S inverse, R inverse, times C, times R, times S, right? And again, this is just substituting this expression for B in the center here. Now, of course, by properties of the inverse, we can express this as the inverse of one matrix times C times another matrix. So again, this is a transitive property. If A is similar to B through S and B is similar to C through R, then A is similar to C through RS, which I'm calling T here. Okay, so again, these three properties are what constitute what's called an equivalence relation, and we're not talking about that anymore today, but as you go on in your mathematical careers, you might talk about this somewhere else. Okay, so here is a property of similar matrices that we saw in the example of 2 3x3 similar matrices, and I'll let you work this out on your worksheet. The theorem is that when A and B are similar, their characteristic polynomials are equal. Okay, so in order to prove this, you'll need to remember that the characteristic polynomial of A is determined by the determinant of some matrix, and you'll have to use the fact that similarity implies there's some matrix S and that's invertible that you can make use of. So I'll let you play around with that a little bit, and we can talk about it more in class. Now, as it turns out, the converse is not true. Okay, so not every matrix that has the same, if you have two, let me rephrase, if two matrices have the same characteristic polynomial, they may not be similar matrices. So here's an exercise that shows that. We can pretty quickly compute the characteristic polynomial of both A and B. Okay, so again, it's pretty quick to show that the characteristic polynomial of A and the characteristic polynomial of B are the same. We'll suppose toward a contradiction that the converse of the previous theorem is true, namely that when two characteristic polynomials are equal, the matrices must be similar. Okay, if A and B are similar, then there must be some matrix S such that A equals S inverse times B times S. Okay, let us call that matrix again S. There's a matrix S such that A is equal to S inverse times B times S. But of course, in this case, B is the identity matrix, right? So if that were true, then A would equal S inverse times the identity times S, which is just S inverse times S, which is just the identity. And certainly A is not the identity in this case. So we see there's a contradiction, and again, this is an illustration that the converse of our previous theorem is not true. Okay, let's go ahead and talk about diagonalization. First, a definition. When A is a square matrix, A is diagonal if Aij is 0 whenever I is not J. Okay, this is a pretty intuitive definition, the definition of a diagonal matrix. A second definition, suppose that A is square. A is diagonalizable if A is similar to a diagonal matrix. Okay, again, since diagonalizable means S inverse AS equals D for some non-singular S, in diagonal D, we see that this is the relationship for diagonalizable. Okay, so here's an example. The matrix associated with archetype B happens to be diagonalizable. So here is an illustration that that is true. And in this case, the matrix S is played by this matrix with its inverse. Here, we see that S inverse times B times S gives us a diagonal form. So the big question then is, how do you cook up this matrix S that does the diagonalizing? And the answer is eigenvectors. So here's a theorem. Suppose that A is a square matrix of size n. A is diagonalizable if and only if there's a linearly independent set S that contains all n eigenvectors of the matrix A. Okay, so this is a pretty cool proof that uses matrix multiplication as linear combinations of columns. Okay, so we'll start with the assumption that S equals x1, x2 out to xn is a linearly independent set of eigenvectors. Let's take the matrix R to be the matrix with those eigenvectors as columns. Now, of course, R is non-singular, right, since its columns are linearly independent. So we'll go ahead and have a look at A times R. Okay, on one hand, A times R should be the matrix with A x1 in its first column, A x2 in its second column, and so on and so forth. Now this is just the matrix lambda 1 x1, lambda 2 x2, and so on and so forth, right? Because the lambdas are the eigenvalues of the matrix A. Now, on the other hand, we can have a look at this matrix a little more carefully. So when we take D to be the diagonal matrix containing those eigenvalues, we can express D as lambda 1 E1, lambda 2 E2, all the way out to lambda n En. So of course R times D is R times that matrix, that diagonal matrix, and we can see that we can write it as lambda 1 x1, lambda 2 x2, all the way out to lambda n xn. Okay, so AR is equal to RD, and we can see therefore that A is similar to a diagonal matrix. Okay, so this proof is pretty cool as it's constructive, and it tells us exactly how to cook up the matrix in order to do the similarity transformation. Okay, the other direction is a little more technical, and I'll leave that to you to read, but here's a take-home message. In order to diagonalize the matrix A, just cook up a matrix containing the eigenvectors of A. And you have to have the right number, right? There have to be exactly n linearly independent eigenvectors, or else A isn't diagonalizable, as it turns out. So here's an example, this matrix F, for which we've previously computed eigenvalues and eigenspaces. So we can take the matrix S to be the matrix of eigenvectors in its columns, and when we go ahead and compute S inverse times F times S, we find that we diagonalize F. So here are those eigenvalues of S that we found together with our eigenspaces. We can see how the eigenvectors fit in the columns of the matrix S. And we know, actually, without even computing S inverse times F times S, that we get the diagonal matrix with the eigenvalues on the diagonal. Of course, those eigenvalues correspond to the eigenvectors in S. Here's the theorem that we'll state without proof, but A is diagonalizable if and only if the geometric multiplicity of every eigenvalue is equal to the algebraic multiplicity. Okay, so this ensures that we have the right number of linearly independent eigenvectors to cook up the matrix R that does the diagonalizing, or the matrix S, as we called it in the last example. So here's an example, this matrix B. We found that the eigenspace of the matrix B associated with eigenvalue 2 is the following. So that eigenspace is the span of the set of vectors containing only one vector, and that one vector is -1, 2, -1, 2. So we see that this matrix B has eigenvector 2 with algebraic multiplicity 3, geometric multiplicity 1. Okay, so certainly this matrix B is not diagonalizable. When A has n distinct eigenvalues, A is diagonalizable. The proof of this theorem is based on a proof that we showed previously, namely that when eigenvalues are distinct, eigenvectors are linearly independent. Okay, so we see that the algebraic multiplicity of each eigenvalue is 1. The geometric multiplicity of each eigenvalue is 1. Those multiplicities are all the same, so that the matrix is diagonalizable. Okay, so here's an example of a matrix A where we're just given that the characteristic polynomial is this quintic polynomial. We can see pretty quickly that the eigenvalues are 0, 2, 1, -1, and -3. So since each of those eigenvalues is distinct, we know that the algebraic multiplicity and the geometric multiplicities are all the same. So there is some matrix R, it's a matrix of eigenvectors, such that R inverse times A times R is a diagonal matrix with those eigenvalues on the diagonal. I won't write in all the zeros, but every other element in this 5 by 5 matrix is equal to 0. A is diagonalizable. Here I've said A, but I really meant H, of course. Okay, sorry for that typo. The matrix H is diagonalizable, and we can put the eigenvalues on the diagonal. Okay, finally, a short trail through the Fibonacci sequences and their representation by eigenvalues and eigenvectors. So a Fibonacci sequence is the sequence of integers where the first integer is 0, the 0th integer, I guess, is 0, the first integer is 1, and the n plus first one is the sum of the previous two. So I'll sort of walk you through this on the worksheet, and we can talk about it in class, but it turns out you can use the power of diagonalization to find a closed form expression for a sub n, the nth term in the Fibonacci sequence. This is a really cool exercise, so I'll encourage you to spend some time with it on the worksheet. All right, folks, that's it for similarity and diagonalization. Hope you've enjoyed learning about how to diagonalize a matrix through a matrix of its linearly independent eigenvectors. Have a great day, and we'll see you next time. So long. Bye-bye.